Section 714 is called solving circuits using power triangle method, or solving AC circuits using the power triangle method. And so we've seen that we can add reactive and active powers algebraically. That's what we were doing earlier. And so we can actually work some circuits now, and instead of having to use the traditional phasor relationships or J notation that we might have used in circuit analysis, we can use the power triangle method and solve some rather complex circuits a lot easier than it would be if we had to use those same methods that we use in circuit analysis. So let's look at an example of that, work through it, and see how we can apply this simple method. So here's a rather complex circuit. This is our figure 717A. And what we're looking at there is we're just given this voltage, and we're given this double subscript notation of this voltage here. It's E21. Okay. And, so what is the voltage between the designation of 2 and 1? That's one thing. And then another thing is try to figure out the current that's going through that 8 ohm inductor. And then another couple of things here is we would like to determine the value of X of C here. We're given that this is 60 volts. So from here to here, we know that is 60 volts. And so, we're going to work a problem, and we're going to do this strictly with power triangle relationships and solve the voltage and currents in these elements that we need to figure out. All right. Now, so what does that look like? Where do we start with this? How do we get going with a problem like that? All right. So let me slide this over, get us a workspace going here. All right, so he says, in this figure, the voltage between 1 and 3 is 60 volts. Okay, so it looks to me like a good starting point is we know from here that that's 60 volts, and, we'll say from 60 to 0, right? And so that, from that point to that point. Now, if that's the case, then really what you're seeing there is 12 ohms and 60 volts. So we can derive some things here to begin with. He says, okay, what are we looking at here? We're looking for the current in each element, okay? We're looking for the current in each element. So we can do this. We know the impedance of the elements for the 60 volts. So we can first, he does the current through the capacitor. I was going to do the resistor, but it doesn't matter. We'll do it like he says. So the current through the capacitor, since it's 60 volts and 5 ohms, then that current there would have to be 12 amps. So if I know that, right, then I can calculate the power, because the reactive power, since it is a capacitor, it's going to be the current times the voltage, which is going to be 720 var. And from our earlier discussions, we're going to call that negative since it's a capacitor. Similar idea with the resistive current. The current going through this resistor is going to be 60 volts divided by 12 ohms, which will give us 5 amps. The active power associated with that resistor will be the current times the voltage, and that will come out to be 300 watts through there. Okay, now, so far so good. Now he says, I want to determine what the apparent power between terminals 1 and 3 are. Okay, well, that is going to be, back to one of our earlier equations, this. And so if I know that, and this is showing you the ease with which this method is used. So if I take negative 720, I square that, I come up with 780 volt amps in terms of the apparent power that is in this branch of the circuit. Okay, so I think I'm just having fun here. But anyway, so that branch of the circuit, the apparent power that is associated with that, and I won't say absorbed or given, I'm just going to say associated with that, is 780 volt amps. Okay, so I cleaned that up a little bit so I can write, because I want us to be able to look at both of these. So here's the thing. This branch of the circuit here, right? This branch of the circuit is supplying that apparent power that we just determined. And there's only one path. And so all of that current would have to flow through that inductor right here. Make sense? All right, and that apparent power that's associated with that is 780 volt amps. Now, I can go back to an earlier relationship for the apparent power. And that earlier relationship says that S is equal to E times I. For this particular situation, we're looking at between terminals 1 and 3. And this current that we're talking about here is this I sub L here. Excuse me. So if I solve this for I sub L, okay, then what I have is S divided by E. I'll put 3, 1 in there. I know 780 is the apparent power. And I know the voltage that's associated with that already is 60 volts. So if I do this division across here, I will get 13 amps for I sub L. So here I have very simply determined the current through that inductor, and I didn't do any complex circuit analysis. I didn't have to do any phasor relationships or go back and forth between rectangular and phasor methods. I just reasoned it out using power triangle. So what else do I know? Well, if I've got 13 amps across here, and that's 8 ohms across there, I can determine the voltage drop across that inductor. And that voltage drop across that inductor would be 13 times 8, or 104 volts, okay? From here to here, that's 104 volts across there. I can also determine the reactive power that's absorbed by the inductor now, and I say reactive because it is an inductor, and that Q sub L is going to be the voltage E23, right? The voltage across that inductor, which is 104, times the current through that inductor, and I come up with a positive 1,352 VAR for that specific inductor. If I'm trying to now determine what the total reactive power is, I could go back to my original calculation, and I think I've erased that though for the capacitor. But we have, and because now we have finished discussing the entire circuit, right? All the components. So the total Q is going to be 1352 minus the 720 that we determined for this capacitive element. And so the total Q it's going to be positive 632 VAR across there. The total active power is that power that's only associated with the resistor. So that remains at 300 watts, which is that. And so now we can determine the total circuit apparent power by saying S is equal to P squared plus Q squared, 300 squared plus 632 squared, square root of that, and I come out with 700 volt amps, which is the total apparent power for this circuit that we're looking at. Okay, now let me clean this up a little bit and we'll finish it. Okay, now, so for this circuit, what we know to this point is we know the active, reactive, and apparent power. We've made all those determinations. So as I look at this section of the circuit, you know, here's the apparent power, here's the current associated with it. So what I can do now, you know, as I look at this circuit, I'm trying to determine what would the voltage be from terminal 1 to 2. That's the one thing I don't know yet. All right, well, S is equal to E times I. 700 equals E, which we don't know, and 13 amps. Solve this for E, 700 divided by 13, and I'm going to end up with 53.9 volts. Well, he writes 53.8 volts. I'm not sure which is correct, but it's one or the other. And so that gives me the final voltage that I need there. And then the last thing that I can do is I can determine the impedance between these two terminals. And that's an Ohm's law relationship that I can calculate if I were, you know, thinking in terms of resistance. You know, that would be voltage divided by current, right? Just to kind of review for you, but we've kind of outgrown that now, right? Because what we're thinking about is an impedance that's equal to 53.9. We'll just stick with that since that's what he's given us. And that's divided by the current of 13 amps. And so the impedance between those terminals would be 4.15 ohms, okay? So very complex circuit that we were able to solve by just using power triangle relationships, our basic equations for apparent, active, and reactive power, and you know, just working through those. And we took something really pretty tough and we worked it out with relative ease. I would say, well, I'll say in terms of compared to doing it through traditional circuit analysis methods. There's example 711, and I'll come back and since it's related to something that's real world in terms of power, we'll come back and work through that one in a separate video.